Students, continuation to my previous class. Now, in the Doppler effect part, we will consider about the effect of wind or medium. Effect of wind or medium uh, in the apparent frequency part. The very common observation is that suppose forget about source, observer, all that stuff. This is how the wind, this is how the sound is moving. Suppose if it is still air, you will write it as speed c. Suppose if it is a flow of wind from the direction of source towards the observer, then the effective velocity will become c plus vw. Same, suppose on still water in the direction of flow, your velocity is x. If the river flow velocity is y, with respect to an observer on ground, your velocity is x plus y. Same thing you are applying over here. Rest everything is the same. Suppose source is moving in this direction, observer is moving in this direction, which is our standard formula. In this case, apparent frequency heard is C minus V naught by C minus Vs. Only thing that I have corrected is for C. Rest everything is the same. Hello. Now you see source moving, observer moving towards each other. Nothing gets affected. This term still remains the same. Only thing is, instead of minus V, you will write plus V naught here. Rest everything is the same. Now for a change, suppose if the wind is blowing in this direction. See, I am giving a standard relation. I am giving you a standard relation. Source is moving like this, observer is moving like this. So apparent frequency in that case, very simple. The effective C term becomes C minus VW. C minus VW. So therefore, apparent frequency becomes C minus VW minus V naught by C minus VW minus Vs times F naught. That's the picture, right? So this is the effect of the wind. Also, this I have already taught you. Source and observer moving, which is a non-collinear case. One more case we need to study. What is that? Now you are moving. Now here you are the source. You are an observer moving in this direction. For your kind information, there is a stationary reflector, a wall, a hill, whatever it is. Now, the problem with observer is he hear two sounds. One, the one which I taught you in my previous class, and the other is source directly sound reaches a reflector, reflector to observer. Two different sounds this one will hear, this observer will hear. Now let us calculate it. This already we know. This is our standard formula. Source to observer is our standard formula. We know already. What is this part? This is the part which we have written here. This one. I mean, whatever that we learned till now is this. Now the question is, this is a source moving with speed Vs towards a reflector. You can take him as a stationary observer. If he is a stationary observer, the frequency heard by him will be in the formula put V naught 0. C by V minus Vs F naught. Fine. Remember, this is the incidenting sound. The reflected sound will also have the same frequency. Which means at this case, this is equivalent to a source, which is stationary, sending sound of frequency F1. Now, this part, remember here, taking stationary source as the reflector, observer is moving stationary source. What is going to be my formula? C plus V naught by C times F1. Don't forget F1 is this. After substituting, I got this relation, which means hereafter, if a source is moving, if an observer is moving towards, or even it is like a mirror question. If you treat him as a plane mirror, observer, object, image, same situation you had, you can see that. Okay, right. So the observer is hearing two sounds now. One, a sound of frequency f dash. Two, a sound of frequency f2. You will hear beats also because they are two different frequencies. Fine. In this case, reflector is taken as stationary. Now, what if the reflector is in motion? What if the reflector is in motion? If the reflector is in motion, again, no issues. Just small modifications is required. No change in this part. I will receive a frequency. I mean, in fact, what do you call this part of the frequency is F2, which is given by source. Imagine he is an observer moving towards the source with VR, not V naught. VR. So what is going to be the formula? C plus VR by C minus Vs times F naught. Now he will reflect. In fact, the reflector will reflect sound of this frequency. Then what about the observer? The observer will receive now a sound note with the frequency, say F3. F3. What is F3? It is what case? Observer and source moving towards each other case. C plus V naught by C minus VR times F2. And you substitute that F2 here. Remember, the major problem with Doppler effect questions is calculation part. Else, everything is clear. Right? So I have covered maximum portion of Doppler effect cases clearly. Right. Now we will deal some numericals. No. One famous problem is there, which I need to discuss. Now now you see a situation where you have sound of frequency. You can see this is a very famous model. Sine 10 pi t, sine 12 pi t, sine 4 pi t. Three frequencies. Morning I taught you, no, previous class I taught you only two frequencies. Now three frequencies. Now, you see the Desmos diagram is what I am mentioning here. Now you modify this, you add this plus this, you will get an equation like this. Overall, you will get an equation like this. Remember, the average of these three frequencies is 12 pi t. So this is the frequency term. Rest is amplitude term. So the amplitude term contains 1 plus 2 cos 2 pi t. So if I plot 1 plus 2 cos 2 pi t versus time graph, A maxima, AB maxima, this is also maxima. Don't feel that waxing is this. Wrong. Waxing, another waxing. This is also maxima only. So therefore, in this case, the interval is 0.5 seconds. And beat frequency is 2 seconds. Okay. So difference of frequencies is almost the same. 10, 12, 10, 12, 14. Don't forget that. So if all the three sounded together, we will get 2 seconds as beat frequency. With the graph I have provided. Very famous model. Right. Now, all these are H.C. Verma questions. Why I am teaching H.C. Verma questions means first you need to understand the fundamental application of these questions. Thereafter, we will go for higher order models. Now, please go through the question. A train approaching a platform at a speed of 54 km per hour. Okay, we'll convert it later into meters per second. And it is a sounding a whistle. An observer on the platform finds its frequency to be 1620. What he heard is 1620. The train passes the platform, keeping the visual marker. It is passing the platform on and without slowing down. What frequency will the observer hear after the train has crossed the platform? Speed of the sound in air is 332. Hold on. You need to do the problem in two different ways. First case, platform and you are rest, means you are a stationary observer. Its source is moving towards you. So what kind of frequency you will hear? Let it be F2. F2 is F0 times C by C minus Vs. Standard formula I have applied. I know F2. I don't know F0. Hold on. Even I don't care whether it is required or not. Now I have the value of F0. Simply, I have flipped this out to here. Just please confirm whether you are clear on this or not. Please check whether you are clear on this or not. I'm just converted this, rearranged this properly. Why? Now, what is the next case? Next case is the case where observer is stationary, source is moving away from stationary observer. In that case, the frequency formula is F0 C by C plus Vs. Always remember the fundamental equation. Don't forget the fundamental equation. Source moving towards observer, Vs, Vo, and speed of the sound. So in this case, apparent frequency is C minus Vo by C minus Vs into F0. Every condition you can derive it from there. You know what is the condition here? Source is moving away from stationary observer. So in this case, what will happen? Observer is rest and away. So instead of C minus Vs, you will have C plus Vs. Hold on. And you know what? Okay, after I have done C given 332, Vs 54 kilometer per hour, when converted into meter per second, you will get 15 meter per second. So I got F0 332 by 332 plus 15, 347. So F0, I have determined F0 from here. You see here, 1620 Hz is F2. So I got what do you call F0 1620 into 370. I'm just substituting the value of F0 over to here. That's all. So therefore, by proper substitution, you will get the answer. Okay. Now I am repeating again. It's a simple question. Direct substitution question. I am telling you again, it's a direct substitution question. Nothing to worry about this. I told you pathetic part in this question is the calculation part. While you are doing, it is a simple calculation based, a calculator based operation. But while you are doing in reality, it is a hectic task for you. Next, this is a very good question. A very good question. Two electric trains run at the same speed of 72 kilometers per hour. Don't worry. When converted into meter per second, you will get 20 meters per second along the same track in the same direction with a separation of 2.4 kilometers. Remember, both the trains are on the same track. Fortunately, they were separated by 2.4 kilometers. The two trains simultaneously sound brief whistles. A person is situated at a perpendicular distance of 500 meters from the track, equidistant from both the trains at the instant of whistling. If both the whistles were 500 Hz, speed of sound is 340. Find the frequency heard by the person. Remember, if you imagine the observer here, at the instant when the train is heading towards the other, at this instant, whistle was blown. Similarly, while it is passing in this mode, whistle was blown. Remember, this is 500 meters, 2.4 kilometers. Let this makes an angle theta. If this is a theta, the component is V cos theta. Now, what is F1? One that receives from this observer is F1 given by C minus Vs cos theta. F2. F2 is F0 C by C plus Vs cos theta. The first one moving towards theta. The other one, this is also theta, but the component is away. This component is away. V cos theta is away. F2 is F naught C by V plus V cos, C plus Vs cos theta. Now you got two different frequencies. You may ask me how to find cos theta. You said they are separated by 2,400 kilometers. This is 1,200 meters. This is 500 meters. And what is, this is hypotenuse. Root 1,200 square plus 500 square. So cos theta is 1,200 by root 1,200 square by 5 square. So you have every data. They have given F naught also. This is F naught. Just substitute it. Okay. Earlier, I have given you the best theory. That's fine. Next, another H.C. Verma question. All these are H.C. Verma questions only. Very good questions. Really very basic level. You can see that in figure, you have a similar model, but a different approach of solving. In this figure shows a source of sound moving along the x-axis at a speed of 22 meters per second, continuously emitting sound of frequency 2 kilohertz, which travels in air at so-and-so speed. Can you spot listener Q in the question? Yes. On the y-axis. Here he is. And he is at 330 meter from the origin. At t is equal to 0, the source crosses the point P. Right. When does the sound emitted from the source at P reach the listener Q? First question. What will be the frequency heard by the listener at that instant? Next, where will be the source at this instant? Good question. While the source is crossing, it produced sound. These sound waves reaches Q. Fortunately, please try to understand, if he is producing sound at this point, Doppler effect will be missing. You know why? Doppler effect, relative motion is not there along the line joining P and Q. The entire component is perpendicular to PQ. It hears the actual frequency of the train engine. Now you see, any sound that starts from here travels at a speed of 330 to reach 330 meters. It takes 1 second. At t is equal to 1 second, frequency of sound heard is 2 kilohertz. Why? Because it is 2 kilohertz. No effect of no Doppler effect in this case. I'm telling you, Doppler effect is not applicable under two conditions. Condition one, if source is moving at right angles with respect to observer, Doppler effect will be missing. Two, if the speed of source or speed of observer exceeds the speed of sound, you cannot apply Doppler effect. Only for very small values, you can apply Doppler effect. They should never exceed the speed of the sound. Right. Now, by the way, what is the speed? The speed is 22 meter per second. You are traveling at a speed of 22 meter per second, and it took 1 second by the sound to reach Q. In 1 second, you will travel 22 meters. Right. What will be the frequency heard by the listener? Where will be the, I think I've answered all. Right. Next. One more point in this question involved is, suppose the source horned here, you are hearing the sound here, right? Like I said, you are producing sound over here, and that sound is heard by you at this point of time. Right? To travel this part, it took say t seconds. So this distance will be 22 t. We know already this distance. So this distance is covered at a speed of 330. Now issue is, you have a right angle triangle in terms of t, in terms of t, in terms of t, in terms of t. I got t here. Right. I got a t. You want cos theta term, fine, no issues. I can give you that. Now the issue is, whatever that you are honking over here, that sound I will hear as F naught C by C minus V cos theta. Cos theta can be written as 22t 22t by 330t. You will get 22 by 330 here. You need to do proper calculation to close this. Concept is important, very important. No, concept is very important. In this question, there are two parts. Don't forget that. What are they? See, in this question, when it honks here, what time it took to reach Q? In that time, what distance it traveled? They have asked. Other thing, while I am crossing this point, see, please try to understand. While I am crossing this point, somewhere I would have produced a sound. And you heard that sound exactly when I am crossing here. That part is also involved in this question. This question contains two different parts. Remember, such models are expected even in advanced exam also. A very good model. Basic model, otherwise. A very good question. Again from H.C. Verma. Right. Go through the question. A car moves with a speed of 54 kilometer per hour, means 15 meter per second, towards a cliff. The horn of the car emits sound of a frequency 400 Hz, right? The natural frequency at a speed of 335 meter per second. That is the speed of the sound. Find the wavelength of the sound emitted by the horn in front of the car. Hold on. I just say source, moving, C, moving. I have given you this relation in the first class itself. Apparent wavelength in this journal is C minus Vf by F naught. In this journal, it is C plus Vs by F. That is the first question, and I have done. Next, second part. Find the wavelength of the wave reflected from the cliff. No issues. Whatever the wave that strikes the reflector, stationary reflector, it is the same that gets reflected back. See, if a stationary observer finds incident sound is of lambda wavelength, reflected sound is also of lambda wavelength. So second part is also done. Next, third part. What frequency does a person sitting in the car hear for the reflected sound wave? Who is the observer? The source, he himself is an observer. Hold on. Don't worry. Whatever the sound that you produced, he is a stationary observer at that time. He will hear with a frequency F1. You know how to handle this. This is the formula in that case. This is the formula. F1 is equal to F naught C by C minus Vs. Pakka stationary. It will reflect the same frequency. Now the question is, you are the observer now. You are the observer moving with the speed Vs, hearing to a sound F1. This is a stationary observer. Then what happens? Don't confuse with the formula. Vs is the speed of the observer in the car. The hears a frequency given by F1. See, observer moving towards the stationary source. So C plus V observer by C. Here the observer is observer in the car himself. So that you will get as both together you take, you will get here as C plus Vs by C minus Vs. I have done that calculation part. You will get 437.5 Hz. Remember, one more point. This is 400 Hz. In a car which you are sitting, you hear the sound of the horn directly as 400 Hz. But the reflected one is of 437.5 Hz. So maybe you cannot hear, but an instrument there can detect 37.5 beats per second. The human ear may not detect. I told you in my previous class, an instrument can detect 37.5 Hz. Okay? Right. What was given? How many beats does the ear in 10 seconds? Between the sound coming directly from the horn and that coming after the reflection per second, 37.5 hertz. And so this is the next part of the question. Again, this is from H.C. Verma. A train running at 108 km per hour towards east whistles at dominant frequency of 500 Hz. Okay. Dominant means that is the major frequency. 30 meter per second. 108 km per hour is equivalent to 30 meter per second. Speed of sound in air is 340 meter per second. What frequency will a passenger sitting near the open window hear? It's a common sense question. Open window is nothing but he is hearing to his engine driver who is honking that particular sound. So there is no relative motion between the engine and himself. So therefore, no Doppler effect. So he will have straight away here 500 Hz. What frequency will a person standing near the track hear, whom the train has been just passed? It is as same as stationary observer, source moving away. Just now we have done the formula for that. F is equal to C by C plus Vs F naught. Now, till this point is a normal, very calm question. A wind starts blowing towards east at a speed of 36 km per hour. Which direction train is traveling? Train is also traveling in the eastward direction. Right. Right. Calculate the frequencies heard by the passenger in the train and by the person standing near the track. Only difference here is, I told you again, for the passenger, who is sitting in the train, now the formula gets converted as C minus VW minus Vs by earlier. Observer and source are moving with the same speed. Only difference is effective value of C, you will take it as C minus VW. Rest everything is the same. Even in this case also, since there is no relative motion, the person hears the same frequency. Same frequency again. Okay? Person in the window, hearing the sound from window will hear the same frequency. Next. This is one more, I think it's the last question of H.C. Verma. A source emitting a sound of frequency nu is placed at a large distance from an observer. The source starts moving towards observer. See, till now you have seen constant velocities. Now is acceleration. Find the frequency heard by the observer corresponding to the wave emitted just after the source starts. If not this term is involved, it's a very complex question. Just after means one time period. One time period. Okay, fine. You would have traveled a distance of half AT square by this time, and you will call this as a lambda apparent. So what is lambda apparent? Lambda apparent is lambda naught. Morning, I have written this part as a CT. Now I am writing this part as a different thing. Remember, morning, this is the actual wavelength. And this you have written as Vs into T, right? And this is a lambda apparent. Now I have modified it in this form. T, one time period. One time period means reciprocal of frequency. So A by 2, 1 by F naught square. So you got lambda apparent value as this. Okay, any doubt? I am telling you, find the frequency heard by the corresponding to the first wave. The wave, first wave emitted just after the source starts. First wave means in one time period. So this is lambda apparent. And fortunately, observer is rest and he hears the sound at a speed equal to the speed of sound. C by lambda apparent. 2C F naught square by 2C F naught minus A is what the frequency the observer here. It's a very famous model, my dear friends. A very famous model. So please listen to this carefully. So basic models of Doppler effect I have done. And complex models of Doppler effect I will take care tomorrow. Tomorrow I'll take care complex models of Doppler effect. Okay? Right. With this, I'll close this class.